There's a place in the universe where the laws of physics don't just bend, they break. Where our finest equations, the ones that put humans on the moon and predicted ripples in space-time, suddenly spit out a single, useless answer: infinity. Plug in the numbers, and the maths returns nonsense. Density, infinite. Curvature, infinite. Volume, zero. Physicists have a name for this place. They call it a singularity. And here's the uncomfortable truth they don't always say out loud. A singularity isn't really a thing we understand. It's a giant flashing sign that says, our knowledge ends here. So what is a singularity, really? Let's find out. The word singularity gets thrown around constantly. In science fiction, in headlines, in late-night conversations about black holes. But most of what people picture is wrong. A singularity isn't a tiny, super dense ball sitting at the center of a black hole. It's something far stranger and far more honest about the limits of what we know. In the next few minutes, we'll clear away the myths. We'll see where singularities actually come from, why there isn't just one but two great kinds, why infinity is a warning rather than an answer, and what some of the boldest physicists alive think is really going on. Let's start by correcting the picture in your head. Let's bust the myth first. When most people imagine a singularity, they picture a marble, a minuscule, impossibly heavy pellet. But that's not what the theory describes at all. According to general relativity, Einstein's masterwork on gravity, a singularity is a point where matter is crushed to infinite density and zero size, and where the very fabric of space-time curves infinitely sharply. The trouble is, infinity isn't a physical measurement. You can't weigh it, you can't visit it, you can't build a sensor that reads infinity. So a singularity isn't best understood as an object in space. It's better thought of as the place where our description of space and time simply stops working. To see why that happens, we need to look at where the equations send us. So where do these monsters come from? They fall straight out of Einstein's own equations. Take a giant star that runs out of fuel. With nothing left to push back against its own weight, gravity wins, and the star collapses. The more it shrinks, the stronger its gravity becomes, which makes it shrink faster, which makes gravity stronger still. It's a runaway process with no obvious break. Follow the mathematics all the way down, and it doesn't stop at a small, dense core. It keeps going, to zero size and infinite density. The equations, in other words, predict their own breakdown. For a long time, physicists hoped this was just a quirk, that real collapses would be messy and lopsided and would somehow avoid this absurd endpoint. Then one man proved otherwise. In the 1960s, the physicist Roger Penrose asked a sharper question. Forget perfect, idealized spheres. What about real, messy, lumpy collapses? Could they escape forming a singularity? His answer, which later earned a Nobel Prize, was startling. Using powerful geometric reasoning, he showed that once a collapse passes a certain threshold, a singularity is essentially unavoidable. It isn't a fluke of tidy maths or a flaw in the setup. Within general relativity, given reasonable conditions, these breakdown points must form. That was a turning point. Singularities went from being a suspicious oddity to being a firm prediction of our best theory of gravity, and that raised the stakes enormously. Because if the theory insists they're real, then the theory is also insisting on its own limits. And there isn't just one place this happens. Here's something that surprises a lot of people. The singularity inside a black hole isn't the only one. The same mathematics points to another, at the very beginning of everything. Rewind the expanding universe like a film played backwards. Galaxies rush together, the cosmos grows hotter and denser, until, around 13.8 billion years ago, everything converges toward a single, infinitely dense state. That's the Big Bang singularity. So we have two flavors. One lies in the future of anything that falls into a black hole, hidden away in the dark. The other lies in the past of the entire universe, the apparent starting line of space and time themselves. Different settings, same problem, a point where the equations hand us infinity and refuse to say more. Which forces a deeper question: should we even believe it? Here's the crucial mindset shift. In physics, when your equations produce infinity, that is almost never a discovery, it's a symptom. It usually means your theory has been pushed beyond the range where it works. History is full of examples, theories that blew up into infinities, until a deeper theory came along and tamed them into sensible, finite answers. Most physicists suspect singularities are the same story. The infinity isn't telling us the universe contains a literal point of endless density. It's telling us that general relativity, magnificent as it is incomplete. It governs gravity beautifully on large scales. But at the unimaginably tiny scales of a singularity, it must hand over to something else. The problem is, nature seems determined to keep that something else out of sight. Notice something convenient, and a little eerie. In a black hole, the singularity is always wrapped inside the event horizon, the boundary beyond which nothing escapes. That means we can never actually see one or receive any signal from it. Penrose captured this in an idea called cosmic censorship, the conjecture that nature always hides its singularities behind horizons, so the breakdown never spills out into the wider universe where it could wreck our ability to predict anything. A naked singularity, exposed for all to see, would be a genuine nightmare for physics. So far, the cosmos appears to keep its most broken places sealed away in the dark. It's an unproven hunch, but a deeply important one, and it leaves us with the biggest question of all. What's really down there, if not a true infinity? Singularity should be, each flickering in and out as alternatives. This is the living frontier. To describe what truly happens where a singularity should form, physicists need a theory that unites gravity with the quantum world. A theory of quantum gravity. We don't have a complete one yet, but the leading candidates all hint at the same thing, that there may be no true infinity at all. Instead, at the smallest conceivable scale, some new physics likely steps in and halts the collapse before it reaches the impossible. Various proposals replace the sharp singularity with something finite but exotic, a tiny, intensely dense core, or an object woven from quantum threads with no genuine point of infinite density inside. We don't yet know which, if any, is correct, but the consensus is shifting. The singularity is probably not a real endpoint of nature. It's the placeholder we use until better physics arrives. So here's the honest, humbling truth. A singularity isn't really a place we've explored. It's a mirror held up to the limits of human understanding. Every time our equations scream infinity, they're pointing at a door we haven't yet learned to open. And rather than being a failure, that's one of the most exciting things in all of science. Singularities mark the exact spots where our current theories run out, and where the next great revolution in physics is most likely to be born. The people who finally explain what lies inside a black hole, or what truly happened at the Big Bang, will rewrite the textbooks. That frontier is open right now. And it started with the courage to take a single, absurd answer seriously. So let's tie it together. A singularity isn't a tiny, dense ball. It's a point where general relativity predicts infinite density and zero size, and where the theory breaks down. They emerge from gravitational collapse, and Penrose proved they're not avoidable within our current physics. They appear in two great forms, inside black holes and at the Big Bang itself. But that infinity is almost certainly a red flag, not a fact. A sign that a deeper theory of quantum gravity is waiting to be found. Nature seems to hide these breakdowns behind horizons, sealing the mystery in the dark. The truth about the singularity is that it is, quite literally, the edge of what we know.